Hello. So far in supervised learning, we have looked at binary classification and we have looked at the problem of k nearest neighbors, the algorithm called k nearest neighbors to solve the problem of binary classification. We identified an important problem with k nearest neighbors, which is the fact that k nearest neighbors does not learn any model from data. So we asked the question, can we come up with algorithms which, given a data set, learns some interesting model from this data, and once the model is learned, we can throw away the data set and only use the model to make predictions on test data points. Today, now what we are going to see is such an algorithm, which is a simple algorithm, very popular algorithm, it kind of is a base algorithm for several complicated algorithms that we will see later on as well. And this algorithm is what is called as the decision tree algorithm. What's the input to this algorithm? As usual, the input is a data set, which is a training data set, which looks like, as usual, x1, y1, dot, xn, yn, where xi is in d dimension for all data points and yi is in +1 or -1. This is a binary classification problem. Now, what is going to be the output of this algorithm is you take the data set and then output a decision tree. And this decision tree is going to be used to make future computation, future predictions. So, what is a decision tree? A decision tree is going to look as follows. How is the decision tree going to look like? Well, it is a tree in the sense of computer science tree is going to look like following. So, it is a binary tree and it's going to have some nodes. It's a rooted tree. It's going to have a root node, and then you are going to have some internal nodes, and then you are going to have some leaf nodes. That's how a tree typically is. So, in every node, you are going to ask a question. Let's say this is question 1. So, this is a yes or no question, which means the answer to this question can be either yes or no. And now, if the answer is yes, then you ask a different question. Question 2, if the answer is no, then perhaps you ask a different question. Question 3, and so on. Now, what might happen is if the question 2 can have again 2 answers, yes or no, and now if it can still go on, right. So, maybe you increase the number of questions, maybe it's question 4, I am just giving you an example, question 5, whereas question 3 has 2 answers, yes or no, but then you do not further ask any questions, you make a decision here. The green boxes are decision boxes. And what might be the decision? Well, the decision in this case is a 1, and in this case, let us say it's a -1, or for this algorithm, let us say it's 0, right. So, we can simply, doesn't really matter, we can, but I'm just going to use 0 to indicate negative samples. Whereas in the other side, you ask extra 2 questions, and then based on that, you might make a decision. This might be yes, no, this is an yes, no. And now you make the decisions, maybe here it is 1, here it is 0, here it is 0, here it is 1, right. So, these nodes, these guys are called as prediction or leaf nodes. So, this is the tree, right. So, this is, we will talk more about what exactly are these questions and so on, but this is the structure of the tree. It is a binary tree, it's got every root, every node, internal node, all the red boxes are internal nodes, every internal node has a question associated with it, and then there are 2 answers to it, and the green nodes are the leaf nodes or the prediction nodes. So, now how would we predict? Well, the prediction is easy. The prediction is going to be as follows. So, somehow let us say somebody gives you this tree that they have constructed from the data set. Now, you are given a new test data point, let us say X test. Now, all you do is traverse through the tree to reach a leaf node. Now, Y test is the value in the leaf node. What do I mean by that? I mean that, well, you pass the test data point X test to this tree and ask the series of questions, and then if the question's answer for the X test data point that you passed is no, then you go to the right side. If it is yes, you go to the left side, which means that you are tracing out a path in this tree, and every path ends on a leaf node, and the leaf node has a corresponding 1 or 0 associated with it, and then that would be the label that we predict. So, basically what we have done is we are creating a series of questions from our data set, and these questions are enough, we say, to make predictions of test data points. So, the model here, which was lacking in a k-nearest neighbor problem, the model is the tree. Once I have this tree, I don't need the data set anymore. This tree encodes all the information that I need for prediction that was available in my data set. Once I have this, I can throw away the data set and work just with the tree, which is enough to make future predictions for any given data point, right. So, that is why this is a powerful thing, because the prediction is fast, right. So, you just have to go traverse through the trees, answer a bunch of questions, and then out comes the answer. Now, the questions that we have to ask, well, is what are these questions, right. So, how do I build this tree is one thing, but even before we build the tree, we need to ask ourselves, well, what type of questions are we asking, so that we can think about how to build the tree in an efficient way, right. So, what is a question? Well, question. In a binary tree, in a decision tree, a question, you can think of a question as a feature value pair. What does that mean? An example would be, well, feature is height, let us say height, and the value is 180 centimeters. Now, the question that we will create out of this is as follows: is the height less than or equal to 180 centimeters? Maybe this is feature 3, maybe this is some value theta, right. So, in general, it is some feature, and then we are asking, is some feature less than or equal to some value? This is the type of questions that we are going to restrict our tree to have, right. So, once we know what kind of questions we are going to ask, then we need to build this tree somehow from the data set. Now, which means we have to, what we are going to do is we are going to greedily ask questions, right. So, we have to first somehow find what is the best question to ask, and then we will later on try to expand this tree. So, which means we need to somehow have a measure of how good a question is, right. So, what we need immediately then is we have to ask ourselves how to measure, goodness of a question, right. So, so what might be a good way, right. So, this might be a good time to pause and think, how can you measure goodness of a question. So, just to point you in the perhaps a useful direction to think about, instead ask the question, what would be the property of the best possible question, right. So, I have a data set and my goal is to do prediction well. Now, what would be a really good question, right. So, what property should that question have? Well, let's ask this. Let's ask this ourselves. Now, what does a question do to our data set, right? So, remember we have this data set. Let's call this D, right? So, the data set, which is just a bunch of data points of this form x1 y1 ... xn yn. now we ask a question, let us take one particular question, some feature, let us say height is less than or equal to some value, let us say 120 centimeters, 130 centimeters, whatever, right. So, we ask this question. Of course, this is an yes or no question. Now, I can ask this question to every data point in my data set, right. So, and there are two answers, yes and no. Now, some data points will have features where the height is less than 180 centimeters, and some data points will have the feature height to be greater than 180 centimeters. So, which means that this question is dividing my data set into two parts, right. So, there is one part which is DS, I am going to call this the DS part, which is just a data set with maybe the first point answered yes, maybe the 10th point answered yes, x10, y10, dot dot dot, some bunch of points, right. So, it is an yes or no question. So, every point either answers yes or no. So, which means there is a D no also, which has the remaining set of points x2, y2, x3, y3, dot dot dot, and so on, right. So, it's you are separating, right. So, you are partitioning your data set into two parts, where one part answered yes to this question, the other part answered no to this question. Now, what would be an ideal question? A really good question should have what property? Well, the best possible question, it should have the property that, well, I should be able to make prediction by just asking this question, which means when will I be able to make a solid prediction by asking just this question? Well, in my training data, if I ask this question, if height is less than 180 centimeters, and I observe that every data point which answers yes has the corresponding label as +1, and every data point that answers no has the corresponding the label -1, or the other way around, every data point that answers yes has the corresponding label -1, and every data point that answers no has the corresponding label +1, then I know that this is a super good question, because by asking the single question, I am able to distinguish the +1s from the -1s. Everybody who answered yes have the same label, and everybody who answers no have the same label. Then this is a very good question, because this one question is enough to, classify whether the data point is +1 or -1 in my training set, which means that I will hope to do the same thing for my test data point also. If the test data point comes, I will just look at the height. If it is less than 180 centimeters, then I will say maybe +1, otherwise I will say -1, depending on what the data set says. Now, that is an ideal world, right. So, where you have a single super good question which is enough to say divide my data set into two parts, where the labels of one side is the same and the labels of the other side is also the same. But in reality, such a question may not exist. There may not be a single question that you can ask such that you can divide your data sets into pure sets, right. So, when I say pure, it means that the labels on each of these sides are pure, they are exactly the same. Such pure questions may not exist. So, which means we somehow have to measure how good a question is by somehow capturing a notion of impurity for a given set of labels, right. So, I divide it into two parts. Now, I need to see how impure each of these parts are, right. So, or how pure each of these parts are, right. So, I somehow have to measure this, right. So, which means I now have to measure, right. So, what we need is a measure of impurity for a set of labels. Let us say I give you a bunch of labels, right. So, y1 to yn or yk, right. So, the data set can be of any size, right. So, after you ask the question, only k points have answered yes. I need to associate a measure of impurity. Well, these y labels are either +1 or 0. So, we can, for instance, look at the fraction of ones, right. So, we can look at the fraction of ones in my set of labels. I give you a bunch of labels. The question is, how impure is this bunch of labels? I can compute how many ones are there, or the fraction of ones, and that fraction could be any value between 0 to 1, right. So, this is the fraction of ones. Fraction of ones in my set, let us call this value p. Okay. P can be any value between 0 to 1. If p is 1, then that means that all my labels are 1. If p is 0, that means all my labels are 0. There is no ones at all. Now, in both these cases, there is no impurity because the labels are clean, right. So, it is either all ones or all zeros, both are good for us. But the worst case would happen when p is half, right. So, when you have a bunch of labels where 50% of them are positive, 50% of them are 0, then you are still very uncertain about this set of data points, right. So, because you will not be able to say anything concrete about the label. So, the measure of impurity should be highest at 0.5 and it should be 0 at 0 and 1. So, also if I take, let us say, a measure of, if p is, let us say, quarter, right. So, we know it should peak at half. Now, if it is at quarter, that means that 25% there is 1 and 75% there is 0. Now, this situation is as impure as if you flip it, that there are 75% 1 and 25% 0, right. So, there is nothing more sacrosanct about 1 than 0, right. So, which means that if you have 25% ones and 75% zeros, it is as impure as 75% ones and 25% zeros. Your uncertainty is in some sense the same about what label this class belongs, this set of data points. If I had to make a prediction, what would I predict is still confusing, right. So, it's the same amount of confusion you have. So, which means that 1/4 should have the same amount of impurity as 3/4. So, which means any value lambda should have the same impurity as 1 minus lambda. It should be basically symmetric about half. So, one function which has this property which looks like this, right. So, the function looks like this. It peaks at 0.5 and I have drawn it slightly skewed, but then it is symmetric about half, right. So, the values at 1/4 and 3/4 will be the same, it will be 0 at the ends, right. So, one such function is what is called as the entropy function, right. So, we could use many functions which have this property. One popular function that people use is the entropy. Entropy, well, you think of entropy as a bunch of labels, that is what we are trying to find out. Some bunch of labels is just the entropy of the fraction of ones, because that is what determines how pure or impure this set of labels is defined as the following. It is defined as minus p logarithm p plus 1 minus p logarithm 1 minus p, with the understanding that, you know, the convention says that log of 0 you should treat as 0. So, if this is one possible function which captures our notion of impurity, and basically what you would get if you plot here is just the entropy of p. What I am plotting on the y axis is just entropy of p. It will look like this. It is a concave function which looks like this. So this is a reasonable measure of impurity. Of course, there are some information theoretic reasons why this makes sense and so on. We will not get into the information theoretic. In fact, it has it has underpinnings in statistical physics, from thermodynamics and so on. That is where the name entropy comes from, and then which was borrowed by information theory by Shannon, and then for our purposes we can just think of measuring impurity, right. So, some function that measures impurity, that is what we care about. Okay. So what we now have is some way to measure how impure a bunch of labels are, right. So, now we have to use this somehow to come up with a goodness for a question, right. So, that's our goal, right. So, given a question, how good is this question? Now, remember, we had a data set D and then we asked a question. Well, so, we have a data set D and then we ask a question fk less than or equal to theta. It divided my data set into two parts, D yes and D no. This is the yes guys, this is the no guys, this is D no. Now, what I am saying is I have a measure to capture impurity for a bunch of labels. Now, which means I can capture entropy of D, which means I look at the labels in the original data set, and that will give me some entropy. I can look at entropy of ds, right. So, when I say ds, I mean that the fraction of labels which have 1 in ds is what I am computing the entropy for, and I can look at entropy for d no, right. So, for d no. So, these are 3 different numbers that I can calculate, right. So, it tells us how impure d is, how impure ds is, and how impure d no is, right. So, for every question I have these 3 numbers that immediately come out, right. So, the moment I put down a question fk less than theta, I get ds and d no, from which I get entropy of each of these, and I of course have the original entropy of the data set itself. So, but then there are 3 numbers. We need to associate a single number to measure goodness of a question. So, how can we convert these 3 numbers in a natural way to associate a goodness for a question fk less than or equal to theta? Well, one way to do this is, and perhaps the most natural way to do this is the following. You look at what is usually called as, again from information theoretical underpinnings, is called information gain of a feature comma value, right. So, of a question which is a feature comma value pair can be defined as, you know, how much impurity I originally had, which is entropy of the original data set D. Now, I have entropy of ds and I have entropy of d no. Now, I am going to subtract this impurity from some combination of the impurity of ds and d no. Now, what combination I am going to use? I am going to use some combination that depends on how many data points fell on each side, right. So, let us say lambda is the fraction of data points that went to the ds side, and fraction of data points that went into the d no side is 1 minus lambda, right. So, lambda gamma, right. So, I am using the not lambda, gamma is just, you know, how many guys went to ds, cardinality of the set ds by cardinality of the set d. Now, why am I combining this using gamma, right. So, the reason is, so let us say you ask a question and then you divide it into ds, and ds had 80% ones, right. So, now if ds had 10,000 data points, out of which 80% were ones, which means 8,000 points were ones, now that should kind of give us more confidence about the label that we can predict after asking this question than saying you had 100 data points on this side, out of which 80 were 1, right. So, in some sense what we are saying is that we should also measure by how many data points fell on this side in addition to what is the impurity, because the impurity is not going to take into account the number of data points, it is only going to look at the fraction of ones or zeros in the labels, it is oblivious to the number of data points, right. So, both 2 data sets where you had 10,000 points with 9,999 of them as, or 9,900 as ones, is same amount of impure as per entropy as a data set which had 99 out of 100, right. So, but then the same question is able to classify more points, right. So, if you had 9,900 out of 10,000, right. So, you somehow have to weigh that by the fraction of points that fell on each side, and that fraction is gamma, right. So, basically what we are saying is that initially you had some impurity, and how much impurity gets removed by asking this question, right. So, that is why we subtract out the weighted average of entropies of ds and d no, weighted by the amount of fraction of data points that fell on each side from the original impurity. Now, if the question is super good, then both the sides will become pure just by after asking this question, which means that the entropy of ds and d no will both be 0. So, which means the amount of impurity drop would be the entire impurity that we had in the original d, which means your entropy of d minus 0, which means your gain in information or the loss in impurity would exactly be the amount of impurity that you originally had, right. So, the more the impurity that drops, the more information you gain, right. So, because you are able to make prediction better, right. So, information regarding prediction becomes better, and so this is also called as an information gain. So now we somehow have a notion of goodness of a question. So the next natural thing to do is, how can I convert this into an algorithm, right? So we'll put down that algorithm next.